LLVM. If you've written C, C++, Rust, or pretty much any compiled language, you've already used it. It's the framework that turns your high-level code into fast, efficient machine instructions. But LLVM is not just a compiler, it's a toolkit that every modern language uses to get performance right. But what makes LLVM so powerful? One of its secret weapons is called static single assignment, or SSA. It's the key to faster code, better optimizations, and the reason compilers are smarter than ever. Stick around, and you'll not only learn what SSA is, but why it matters. Let's get into it. Alright, let's start simple. SSA, or static single assignment, is a way to represent your program where every variable is assigned exactly once. Sounds weird, right? You're probably thinking, but I reassign variables all the time. Let me show you what I mean. Take the simple code. Here, x is assigned twice. So how can SSA work with that? Here's the trick. Instead of reassigning x, SSA splits it into versions, like x1 and x2. It looks like this. This tiny change, renaming variables like this, is the foundation of SSA. It's a simple idea, but it unlocks huge possibilities for optimization. So why bother with SSA? Why not just work with the code as is? It's because SSA makes optimizations way easier. For constant folding, if you know x1 is always 10, then x2 equals x1 plus 1 is always 11. And you're done. For dead code elimination, if nothing ever reads x2, you can delete it. No guessing, it's obvious. Without SSA, the compiler would have to track which version of x was being read, and that's slow. But with SSA, it's laid out in a clear chain of versions, and the compiler can optimize it in milliseconds. Now, let's talk about the most mysterious part of SSA, the phi function. Here's the problem. What happens when you have a program like this? Look at the x in y equals x plus 5. Which x is this referring to? The one from the if block or the else block? This is where the phi function comes in. It merges multiple possible values into one. So in SSA, it looks like this. x1 equals 10 from the if branch, x2 equals 20 from the else branch, and when you hit the merge point, phi of x1, x2 says, hey, if we came from the if branch, use x1. Otherwise, use x2. And now we have y1 equals x3 plus 5. So how does LLVM use this? When you compile C, Rust, or Swift, the first step is converting it into LLVM IR, and LLVM IR is always in SSA form. For example, this C code would turn into LLVM IR like this. %1 is a variable or a value name, but unlike variables in C or Python, it follows SSA rules, meaning it can only be assigned once. Add I32 to 3 is an instruction to add two 32-bit integers, 2 and 3, and store the result in %1. It makes optimizations like constant folding, common sub-expression elimination, and loop unrolling way easier. Let me explain. For constant folding, since %1 is fixed to 5, the compiler can fold it at compile time. It won't even generate an add instruction for the CPU. It just replaces %1 with 5. For common sub-expression elimination, if another instruction also computes 2 plus 3, it can reuse %1 instead of recomputing it. And for loop unrolling, since assignments are never overwritten, loops become easier to analyze and unroll, where multiple loop iterations are combined into one. There's also simpler data flow analysis. Since variables never change, tracking the definition of a variable is trivial. If the compiler sees %1, it knows exactly where it came from. This makes it easy to detect dead code. If no one uses %1, the compiler just deletes it. And finally, better parallelization. Since each variable is immutable, it's easy for the compiler to see which values are independent, and this helps identify sections of code that can be parallelized. Let's bring it all together. SSA does three things for compilers. The first thing is that it simplifies optimizations like constant folding, dead code elimination, and loop optimizations. Number two, it handles control flow merging, using phi functions to merge variable versions. And number three, it forms the core of LLVM IR. Every C, Rust, or Swift program you compile relies on this concept. Without SSA, compilers would struggle to keep track of variable states. SSA makes it predictable, simple, as well as fast. Here's a little extra for you performance enthusiasts. You've all heard of lock contention. When multiple threads are waiting on the same lock, the critical section size matters. But here's the trick. SSA can help detect which parts of your program are hotspots by tracking where shared data is being accessed and locked. If two threads hit the same phi function at a merge point, you can analyze where contention is happening and rewrite your code accordingly. SSA is not just for compilers, it's for performance tuning too.